You may have seen polar coordinates in a pre-calc class. You may have covered them in Calc 2. Some of you may have covered them in Calc 1. Some of you may have covered them in a trig class in high school. There's all kinds of places where you might have seen it. I just want to hit the high points of what I need. There's a lot more that we could do with polar coordinates. But there is a small amount that I need you to be good with to move on with me to answer some more interesting questions involving integrals. Just bear with me. Points in a plane or in 2D are represented by polar coordinates when you have identified a reference frame that includes a pole, which is a starting point in your 2D system. Now that starting point is looking like the origin up here, and it actually has polar coordinates of 0, 0, just like we have polar, or just like it's 0, 0 in rectangular or Cartesian coordinates. But every point is represented by two coordinates, the first of which is the distance between our point and the pole, and the second is an angle. Now, we can measure angles counterclockwise or clockwise, and we're going to adhere to the same tradition that you have from trig. Counterclockwise, positive angles, clockwise, negative angles. But if you take the line segment, or actually if you take the ray that goes through the pole with an angle of 0 radians, I get to use radians, with an angle of 0 radians, and you swing in a counterclockwise direction till you hit your point with another ray, then that angle you just made is the angle that we refer to as theta in coordinates and polar coordinates. Now theta can again be positive, negative, or 0, and we typically measure our polar angles with radians. Every point in polar coordinates actually has infinitely many different representations, which gets scary. But we'll make it. We'll be okay. We're not going to need to deal with that in what we're going to be looking at, okay? So our angles will range from 0 radians up to 2 pi radians, and we're not going to need to go beyond 2 pi radians. More often than not, our conversion will be from rectangular to polar. Now you may recall from the past having to convert from polar to rectangular, in which case sometimes you had to find out what your theta was and stuff, and using arctangents to do that, or inverse tangents if you like writing that better. We have to be careful though when we use inverse tangent to find an angle, because inverse tangent has as its range 0 to pi. So if we needed an angle that was down here at the bottom, we'd have to make some adjustments. Fortunately for us, the three major things that we need in terms of conversion from x's and y's to r's and thetas is that x is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared equals r squared. That comes from taking my polar point, dropping what you would consider to be a perpendicular down to that ray that's horizontal, and calling the length of that side y, the y displacement. Horizontal displacement, or x, is how I'll label the distance, the horizontal distance between the point and the pole. And so I just made a right triangle. And okay, cosine of theta is adjacent over hypotenuse. So cosine of theta is x over r. So cosine of theta can be manipulated, and I get x is equal to r cosine theta. Sine of theta is opposite over hypotenuse. So y over r is equal to sine of theta. Manipulate, y is r sine theta. And because r is the distance between the pole and my point, here's the pole, here's my point. It's just the distance, which is change in x squared plus change in y squared with a square root wrapped around it. So x squared plus y squared equals r squared. Those are the three that you will need more often than not. I'm not going to need this conversion formula for anything that I do with you, but I put it there just so, yay, you can put it there. Mainly because, excuse me, I'm about to sneeze. Tangent of theta is equal to opposite over adjacent. So tangent is y over x, which means the inverse of tangent, which I like to write as arctangent, of y over x is equal to theta. I'm not going to need it. It's just up here for completion. So you look back at this and say, why she didn't mention theta. Well, okay, it's there. I'm not going to use it for anything. I do need to find areas of stuff. Moving into integrals. As I've already mentioned to you, one of the integrals that we're going to need to do is going to be called an area integral. And when we have x's and y's, and we want to change to r's and thetas, I wonder how we measure area of circular regions like that. We'll figure it out. So when we're in polar coordinates, area is not going to be determined by changes in x and changes in y and little rectangles. Area is going to be determined by little chunks of circular regions. Now there's a formula. I can derive it for you. It comes from geometry, and it's the formula for the area of a circular sector. So you have a circle. There's the center of the circle, the radius of the circle, and a tiny little chunk of the circle where the angle made inside that sector or piece of pi, P-I-E, is theta. So the area of a circular sector is 1/2 times the radius of the circle squared times the angle on the outside for that piece of pizza or whatever it is that you're chopping up. In this picture, the pointy place is at the pole, the radius is the radius of a circle, and the theta is some angle between 0 and 2 pi radians. And it's important when we are measuring distances that you keep your angles in radians, because radians are a measure of distance along a circle. No degrees when we're talking about areas and lengths and volumes, okay? Radians. All right, so up here, let's imagine that I have a polar coordinate system, and now I'm chopping it up with respect to r and theta. Unlike what I would do with x and y, where I chop it up with x's and y's, now I'm chopping up with r's and thetas. And when I chop up with r's, I'm going out more and more. My radius is getting further and further away from the pole. So what you see here is I've drawn one arc to represent one step away from the pole, R1, and another arc to represent a further step away from the pole, R2. Now, right in the middle, I have a point that I've labeled with an R value. That's the average of those two radii stepped away from the pole. Now, because I'm looking at a sector of a circle and I'm in polar coordinates, to make a piece of pi, what I need to do is I need to go up an angle theta 1 and then up some more an angle theta 2 and then find the distance or the difference between those two. And so I'm going to call that difference delta theta for that piece of the pi in polar coordinates. And I'm going to call the difference between my two r values delta r. I'm going to rewrite this region that I've shaded, that I've called delta A. I'm going to rewrite that so that I can find, or redraw that, so that I can find a formula for its area. So what I'm going to do first is I am going to take a chunk that goes from the pole to R1. So there's the pole, there's R1, and using this formula for the area of a circular sector, I can find the area of that piece. Then starting at the pole, going out to the radius that I called little r. Okay, then I can use the formula for the circular sector, area of a circular sector, to find the area of that slice of pi. And if I take the difference between those two, then what I will have is a portion of my delta A. So if I take the area of the circular sector that I get from going out r units from the pole and keeping my angle as delta theta, and I subtract from that the area I get when I go R1 as a radius, but the same angle, then what I will have is a portion of the area that I would get, my delta A, which is my plane chopped up into r's and thetas. But wait, that's not the whole area of that thing that I drew up there. There's another piece. Now that other piece came from starting at the pole, going out to R with an angle delta theta, still the pole, right there. And then, starting at the pole, go all the way out to R2, make the same angle theta, and if I find the difference between those two areas, then I will have this other piece of the area of this thing, whatever you want to call that shape, and that area is found by taking the bigger one, 1/2 R2 squared delta theta, and subtracting off the smaller one, 1/2 R squared delta theta. Now, if I take those two pieces, shade this for consistency. If I take those two pieces whose areas I just represented and add them back together, I get the area of this strange little shape up here, which again is generated by slicing the entire two-dimensional world with increments of r, radius, from the pole, and then incremental changes in theta through the whole plane, so delta thetas. Now, if you look here, I conveniently wrote something in the same color, and if you can't see the color, my apologies, but I have, in the beginning, 1/2 r squared delta theta, and on the end, I have minus 1/2 r squared delta theta. They're going to go away. And if you'll allow me a little poetic license here, I'm going to go ahead and pull out the 1/2 that they all have in common. I'm going to write the r2 squared first, minus r1 squared, and then pull out the delta theta on the end because they have that in common. And now I just can't help it. I see the difference of two squares. I want to factor the difference of two squares. So here I go. I did it. I factored the difference of two squares. Oh my gosh, I had another name for 1/2 of the sum of my two current radii. I called it r. Little r. That's supposed to be actually rearranged. R2, R1, R2, R1, so that I get my SIGN correct. R2 minus R1 is the difference between my radii, my incremental change, my increments of R. We call those incremental changes, well, we denote them with deltas, right? That's delta R. And there's already a delta theta on the end. So, I've already brought up the concept of an area integral. And I haven't done any area integrals with you. I'm getting you ready to do a whole bunch of area integrals. If we stick with the Cartesian coordinate system, we're looking at incremental changes in x and incremental changes in y to get little bitty rectangles in our plane, and we can find their areas by multiplying those little changes in x by those little changes in y. Or, if we feel like it, maybe we want to multiply the little incremental changes in y by the little incremental changes in x. Multiplication is commutative, so it doesn't matter which order. And now, as my incremental change gets tiny for r, and my incremental change for theta gets tiny, small r's, small thetas, turn it into differentials to represent those increments. And now I have a representation of dA, small changes in area, with either x coordinates and y coordinates, or now polar coordinates. I know I haven't given you a context yet. Please bear with me. The context will come. The point is, I'm going to start integrating over regions. And sometimes x and y will be fine because of the shape of our region. Sometimes, however, x and y may not be fine because of the shape of our region. And the region in the xy plane might be, I don't know, very, very circular. And when the region that I need to integrate over, when the base of my shape or the cross sections of my 3D surface happen to be circles, those aren't always easy to deal with in terms of an integral. You get square roots of sums of squares and stuff inside of there. Yeah, no, I promised you no trig substitution, didn't I? I never said no trig. I did say no trig substitution. So when you have circular cross sections or circular regions in the plane that you want to integrate over, we're not going to measure area as areas of rectangles. We're going to measure area as area of these weird little things that looks like very shared pieces of pie. So instead of dx dy or dy dx, we'll measure area with r dr d theta.